What is light? Why does it behave the way it does? Over the centuries, scientists chose models from the world around them to explain light. The particle was the first widely accepted model for light, thanks to Sir Isaac Newton, who first formulated a particle theory to explain several behaviors of light. But there are a few scientists who favored another model for light, the wave. Waves are a traveling disturbance, which transmit energy from one place to another. In the 17th century, all known waves required a medium, such as water. So it was proposed that air, and the space around us, is filled with an invisible medium called ether, in which light waves propagate. About the time Newton was developing his particle theory, another scientist, Christian Huygens, proposed a detailed wave model of light. This wave model more easily explains some behaviors of light. Diffraction, for example. If a tiny slit is made and light shone through it, the edges of the pattern are not sharp. Huygens compared this behavior to diffraction of water waves. If waves are interrupted by a barrier and a gap is made, only part of each wavefront propagates through the barrier. As the wave passes through the gap, it bends around to either side. Huygens proposed that in the same way, light bends around the edges of a slit. This produces a fuzzy edge created by bands of dark and light lines. Huygens used waves to explain several other behaviors of light, including geometric reflection. When a mirror reflects a light beam, the angle of incidence always equals the angle of reflection. Water waves behave the same way, although their behavior can appear confusing. Note the direction of propagation to the wall and away from it. The angle of incidence is equal to the angle of reflection. Huygens also used water waves to explain refraction. When waves move from deep water into shallow water, they change direction and slow down. The result is a change in the direction of wave propagation towards the normal. In much the same way, a beam of light changes direction as it passes from air into water or glass. Huygens reasoned that if light is a wave, since it bends towards the normal, it must move slower in the new medium. His prediction contradicted Newton, who felt light particles, attracted by the pull of the surface, must move faster in water. Huygens' explanation of these and other behaviors of light were just as convincing as Newton's, but Huygens lacked Newton's reputation. Largely for this reason, his wave model of light was neglected for more than 100 years. But slowly, evidence began to mount in favor of the wave model. A major breakthrough came in 1802 when Thomas Young confirmed the existence of light interference. Interference had been considered a weakness of the wave model of light. When two sets of waves intersect, a characteristic pattern of peaks and troughs is created. Critics of the wave model pointed out that this interference cannot be seen when two beams of light intersect. But Young proved them wrong by using a pair of tiny pinholes very close to each other. His experiment also works with two narrow slits and is a little easier to visualize. If light is shone through these slits and projected onto a screen, a pattern of light and dark lines can be seen. This interference pattern can be explained by using water waves. If a barrier interrupts the waves, any slit in the barrier acts as a point source of the waves. Two slits create an interference pattern. The intersecting crests of the waves migrate outward along fixed lines. At each crest intersection, the two waves interact. They reinforce each other to increase the amplitude of the wave. This is called constructive interference. Constructive interference also occurs when two troughs meet. When crest meets trough, destructive interference occurs. The waves cancel each other out and create a dead spot in the wave pattern. And so two slits produce lines of high amplitude caused by constructive interference. And between them lines of zero amplitude caused by destructive interference. This wave interference pattern nicely explains the light pattern created in experiments like Young's. In 1850, there was yet another boost for the wave model. In that year, Jean Foucault successfully measured the speed of light in water and found it to be slower than in air. This destroyed Newton's particle explanation, which required light to move faster in water, and confirmed the wave model prediction that light moves slower in water. These experiments and others gradually eroded support for the particle model. By the mid-19th century, the wave model of light was triumphant.